I think we can start. What we're going to do in the next couple of weeks, pretty much until the end of term, with the exception of a couple of revision sessions, is a very basic introduction to game theory. Okay? So in game theory, we study games. What is a game?
Players.
Game is players. No, games is yes. So okay, so it's kind of hard to say exactly what a game is. And you can say many different things about a game. And yes. Yes, you said players. Did you say players?
I said has players.
Oh, it has players.
Yeah.
Yes, that is great. So
I checked it as well.
Liz and Tim are players. And this is a game. And you still don't know what a game is, but this is one. Okay, now I don't know what I'm going to say. Can you read it all right, or is it not good enough? I think it's the projector is a bit. Is it okay? Light up bright so I can see you. Okay, so if I do that. But then everybody's going to fall asleep. Oh, that's okay. So Liz and Tim are players. Now, Liz has two options, right? She can hide in the house or hide in the garden. That's what it says. But these things are also called something. So A, hide in the house. B, hide in the garden. Lizards, what are called actions, or they're also called strategies. Both words can be used for this. So now you're starting to understand what a game is. A game is something that has players, and each of the players has several actions that they can do, that they can take. That's a good start of understanding what they are. And, I said both players have actions, so also Tim has actions. A. Look in the house, B, look in the garden. Okay, so if you want to know a game, we have to know the players and we have to know their actions. But that's not everything. we have to know what the players want as well. Okay. So, for example, if Liz hides in the house and Tim looks in the house, okay, that's one possibility. And another one is Liz hides in the house and Tom looks in the garden. Which of these two possibilities do you think Tim will prefer? I'll say that again. First option, Liz hides in the house, Tim looks in the house. Second option, Liz hides in the house, Tim looks in the garden. Which of these two options does Tim prefer? House? Yes. Probably. So we know that that Tim prefers house. It could be that Tim is a very altruistic player, and maybe it's Liz's birthday, and Tim wants to lose, and in that case, Tim would prefer looking in the garden when Liz is in the house. Okay, but we are assuming that we know what Tim wants. So in this case, we kind of think that Tim wants to win. Okay, and we will base that on, well, our analysis on that. Now, so you see, what we had was Tim prefers house to house garden. So he doesn't prefer looking in the house to looking in the garden. He only prefers looking in the house if Liz has hidden in the house, right? So it's not like, so his preference is not for one of his actions, but his preference is for the whole pair of actions, both Liz's and his. So we have to know both of them to know the preference. So the both of them is called an action profile. So an action profile is a pair of strategies well, one for each player. Okay, so for example, what we have what do we have? We have house. Yeah, we have house garden. We have garden house, and we have garden. Okay, so there are 4 different action profiles in this game. That's a definition. Well, that's not a definition. The definition is the first 2 lines, and then the 3rd line is an example. But you get that. Okay, so the preferences of Tim or Liz, they both have preferences, but their preferences among these 4 profiles. Okay, so what I'm going to write is that players have preferences. And we have to know players' preferences, otherwise we can't do anything about the game. Okay, so we know that. So in our example, Tim, we said Tim prefers garden to garden house. And if there are 2 action profiles that Tim doesn't care which is better than the other, that's called indifferent. Okay, so Tim is indifferent between garden house and house garden. Okay, it doesn't. I mean, again, this is kind of these things. We're trying to distill the mathematical core of the game, really, from the real life situation, which is a very simple and naive real life situation. But we'll see later some examples where these things are actually, well, these things are actually important. I didn't say that because I wanted to jump right into it. In studying economic behavior of people and so on and so on, there's a lot of game theory there, but I just want to start with the basics and simple things. Okay, so perhaps Tim is indifferent between these two options, but maybe, you know, so that's what we're assuming, but maybe in some situations he wouldn't be, because maybe it's raining, so he doesn't want to go to the garden. He would go there, okay, if Liz goes there, but he certainly wouldn't go there if she, well, you know, so he would actually prefer looking in the house and losing to looking in the garden and losing if it's raining. That's an example. But we're assuming that we know these preferences and know this. So we assume we know the preferences. Of both players. And these preferences are usually expressed by what is called a payoff function. So is used to express a player's preferences. And it's a function which to every action profile assigns a number. Okay, and the higher the number, the more preferable that option is for that player. So, for example, we could have possible payoff function for, who was he, Tim, is, well, on the garden, it's 2. On house, it's 2. He likes that. On garden house, it's 0 because that's less preferable. And on house garden, it's also 0 because he's indifferent between these two outcomes. Okay? Yes.
Is the 2 arbitrary?
Yes. The 2 is arbitrary. Okay? So, in fact, what we want from the payoff function is only that the preferable outcomes have a higher value and the less preferable outcomes have a lower value for the moment. We will want more soon. But, so these things are a little bit fuzzy because there's a big theory of rational choice where scientists study how people make decisions, and so it's sometimes not very clear how it works with irrational people. Right? But so we could do some mathematical analysis on these things. We're assuming that everything works nicely. Okay, that's an assumption. Right? That's what mathematicians make most of the time, and surprisingly, it turns out to be useful in practice, even though these assumptions are not exactly satisfied all the time. Okay, so what am I doing? So give me a possible payoff function for Liz. Has everybody made one? Oh, do you know everybody's made one? Okay, give me one.
Is it just the inverse? So obviously, that's option Tim is going to be the worst option.
Well, in this case, it turns out to be yes, but so that's a great question. Stop. The question is it just the inverse? So what kind of inverse do you mean? Like
So,
minus
switching, the switch.
Yes. So that's quite okay. So that's the next slide. But you have it in front of you, so you're cheating. Okay. So what happens is that in fact in this situation, these things are somehow okay. You can see that Liz actually prefers not to be caught. Okay. So you can think of arbitrary values again, and so maybe this is 3, and this is 3 because like this, Liz is winning something, and maybe this is 0, and maybe this is. It doesn't have to be 0. It can be minus 50. It can be any number really, but it has to be less than the number for the bottom 2. Would you please keep the noise down at the back? Thank you. Okay, so are there any questions? This is quite simple. It doesn't matter what it is, but because we're assuming that not being caught is better for Liz than being caught, the number for not being caught, which is the bottom 2, where's my pointer again? Which is the bottom 2 game profile, action profiles, must be larger than for the top 2, and between them, it doesn't matter for Liz. So if she was getting more money, for example, for hiding in the garden and not being caught, then this would be larger than that. But she's getting the same amount of money, so she doesn't count. Okay? So the next... right, so far so good. So if you have a game where there are only 2 players, like the one we've seen, there can be games that have more than 2 players. If we have a game where there are 2 players, what we can do is put the payoffs in a matrix. Okay, so one player will have the rows of the matrix, and the other player will have the columns of the matrix, and it will look, for example, like this. So now I don't know if I can draw it properly. So we had, okay, so Tim for, okay, so, oh dear. So we'll have a matrix. And Tim can either go in the garden or in the house. And Liz can also either go in the garden or in the house. And okay, so if garden, then Tim's payoff was, we said 0. Yeah? No, Tim wins garden. Can't remember. What was it? Garden means Tim wins. So Tim is earning, we said it was 2. Well, it can be anything. So we have a 2, and Liz doesn't like it. Okay, so and here it was 0 and 3. and here it was 0 and 3, and house was 2 and 0. Okay? So Tim is the row player. And Liz is the column player then. But in fact, it doesn't matter. We could have done it the other way around. So it's just an arbitrary choice. Could have been the other way around. Just make your choice and stick to it. But what is usually the case is that, what we will definitely stick to is that the row players' payoffs come first. Okay, so the row players' payoffs come first, by which I mean that when you look at for garden, there is 2, 0. So the 2 is Tim's payoff, and the 0 is Liz's payoff. Okay, that's the choice we make forever, and this is it. Now, read the definition while I'm not doing anything. Okay, test question. Is this a 2-player game then? Sorry, it's a 2-player game. Is this a zero-sum game? No? Okay, so let's talk about so who thinks this is a zero-sum game? Who thinks this is not a zero-sum game? I have good news for you, because this both answers are in some sense correct. And the sense in which they're correct is if I accept this definition, then it's not a zero-sum game, because here they sum to 2, here the sum is 3, here the sum is 2, and here the sum is 3, so it's not the same everywhere. But I can fix it. So the game can be fixed to be a zero-sum game. Because as I said before, there is nothing special about picking 2 and 0 and picking 3 and 0. And if instead of the 3 for Liz, I picked 2, then I would have a zero-sum game. And the preferences would be exactly the same. Okay, so the preference is not as the values of the payoff function, but the preference is as in which of the outcomes is more preferable to the players would remain the same. So I can do it by, and I'm going to do it. Oh, no. So this will now be 2, and this will now be 3. No. What's wrong with me? This will be 2, and now we have a constant sum, which is the same, so that's good. Yes.
Does that mean that every two-player game can be turned into a zero-sum game?
Does that mean that every two-player game can be turned into a zero-sum game? No. Okay. You seem to have very smart questions today. Excellent. So, no, but you're always one question ahead. You should ask now. Ask me a different question, okay? Do you want to know which one? Please ask. Can you ask me a question? Why is it called a zero-sum game if they sum to 2, not 0? Any questions? Yeah.
Why is it called a zero-sum game?
Oh, because in any zero-sum game, when they sum to anything, you could just make it a zero-sum. So if you could keep the same preferences again if you put 1 minus 1 and minus 1 1 and minus 1 1 and 1 minus 1 like this into a matrix. Okay. Then you make the sums 0, and you keep the same preferences as there were. So the definition says the same number, but it can always be, but that same number can always be made 0. Okay, without changing the preferences. Great question, thank you. Okay. Now the next question is, okay, so is every two-player game zero-sum game? And we'll see some games that are not. I don't know if this is a zero-sum game. No. Is it? Okay. Okay. So this is not a zero-sum game. I don't think it is. But that's not the main question. Okay, so the problem is that if you look at the matrix, okay, there are a couple of problems here. But one of them is this profile of both special offers. Both players prefer that to no special offers. Okay, and that doesn't happen in a zero-sum game. In a zero-sum game, when you have two different outcomes, then you can't, because there's no way. Because if this is preferable to that for both of them, then the sum here must be larger than the sum there. Simple. Okay. There is another problem, which is that it says that the payoff matrix is in thousands of pounds. So yeah, really. Because we said it's just a number which expresses whether something is more preferable to something else. But I took this example from somewhere, and it doesn't really. So yeah, you can kind of say in thousands of pounds, because for businesses, having more money is always preferable to having less money. But it's dubious. So these things in thousands of pounds, well, it's kind of dubious. So let's just think this is the payoff matrix, which it is. Okay? And so what's going to happen here? So right. So what did I do? The Royal Oak is the row player. And the Bull's Head is the column player. Okay. What do you think the Royal Oak is going to do? Introduce a special offer or not? Based on the payoff matrix. Oh, you didn't get the handouts. Where are the handouts? Send them down. Or have we run out? Everything is based on the assumption that everybody gets all these tables already in front of them. Copy that. Sorry, I don't know. This is because more people turned up than ever before this year. So I'll learn a lesson and I'll bring 10 more next time. Okay, so yes, why? Why is the Royal Oak going to introduce a special offer? Well, because they cannot lose, can they? So the Royal Oak, the row player, that's the first number in the payoff matrix in each of the entries. If they introduce a special offer and the Bull's Head does not, okay, then they're winning. Then the payoff is 100, and if they don't, it's 35. So if Bull's Head has no offer, they're better off introducing a special offer. And if Bull's Head does introduce a special offer, then the Royal Oak is also better off introducing a special offer. So no matter what the other player does, they're always better off doing a special offer. And so they're just going to do it because If they didn't, they would be losing money. Okay, so no matter what B does, R is always prefers to introduce the special offer. Okay, so we say that no special offer is a strategy which is dominated by the other one. For R. So no matter what B does, we don't want to do a special offer. Okay, now if you look at what Bull's Head is going to do, they're also always better off introducing the special offer. So the same thing, no offer is dominated. No? So that means that this is what's going to happen. Now we've game. The conclusion is that everybody's going to introduce a special offer. Is that clear? Any questions? Yes.
Does that then mean that no matter what the game, the team needs to find the dominant strategy and then to apply it?
Well, but sometimes, so yes, what is the aim? Who's aim?
When you're analysing a game.
Okay, so when you're analyzing a game, yeah, but it's not always, possible, right? So there's no domination between Liz and Tim. So, but it is a great question. So, I don't know. I'll go back. No, where am I going? I don't know where I'm going. I have no space here, so I'm not. So I can't. So what is the aim of analyzing a game? Okay, so the answer is we're getting there, step by step, and the first step is to look for dominated strategies. Dominated action. So the dominated strategies will never be chosen by a rational player, okay? Because they just don't. No, they don't want to play things that, no matter what the opponents do, they cannot win. Kind of a simple idea. Okay. However, even when you so sometimes you can't find dominated strategies. For example. The first example we had, Liz and Tim. For Liz, there is no dominated strategy or no dominating strategy because no matter where she goes, depending on what Tim does, she can always lose. Okay, so there is not one which would guarantee to be better for Liz, no matter what Tim does. Okay, so you can't always find dominator strategies, and if you do, even if you do find some dominator strategies, that doesn't mean that there will only be one left. So the games we've been looking at were very simple in that there were only 2 possible strategies for each player, but there can be many more. So yeah, so the first step is to find a dominator strategy. Yes.
Does that mean that, depending on the game, there's a game where both players start with a separate thing, and each player might have their own dominant strategy. So one player might have, say, dominant strategy A, or so might have another dominant strategy, but different to player A, since they start at different positions.
Oh yes. Okay, so this is another. So my examples are really stupid, right? I mean, this is already completely okay. The question doesn't make sense. I mean, it does make sense only because my examples are stupid. So it's not true, in fact. So in this case, it looks like the 2 players have the same set of strategies. So it only looks like that, though. But it's not really that, because Liz's strategy was to hide in the garden and hide in the house, whereas Tim's strategy was to look in the garden or look in the house. So they're not the same thing. But they could even be completely different and, well, I don't want to say unrelated, because they have to be somehow related in the game. But they could be a completely different set of strategies. Okay? So you have, yeah, I don't know. What's an example? So I have an example. No, not really. I mean, they always have to be somehow related, but you know. But yes. So of course, so yes, of course, the strategies could be very different. Okay, now I got lost a little bit, thanks to your questions. But it's not a bad thing. This is just a summary of the things we had. What is a game? What are players? What we were looking at is called a strategic game, which is where the 2 players choose their actions unrelated, well, unaware of the other player's decision, and then they play. But there could be things like turn-based games, where they make 1 turn each, etc., etc. So we're not looking at those. We're just looking at a very small part of game theory here. So we'll mostly be concerned with strategic games, where both players make a decision independently and then they act. I said what strategies were and actions. Said what an action profile is, payoff function, zero-sum game. Okay, we know all that. Can you think of any more examples of things that are amenable to being analyzed as games? Shout them at me.
Stock market.
Stock market. Well, stock market. Well, okay. That's a hard one. So who are the players?
Traders.
What are their actions?
Buy or sell.
Yeah. Or at what price they sell, or what price they offer, and things like that. Yeah, that's a whole bunch of different games that go on there. Yes. Something easier. Weapons. Something easier.
Chips.
Uh-huh. Chess is a game. That is correct, but not strategic. Okay, so in the sense that the players don't move simultaneously in chess. So yeah, so it is an example. It's yeah, that's right. It's a good example of a game, but it's there are turns and they move and so on. So that's a sequential type of game. Okay, I've got some more. Unless you want to. So one of them is, for example, a footballer taking a penalty kick. Okay, versus the goalkeeper. For sports fans, if there are any. Because essentially, the kick taker has to decide where to kick the ball, and the goalkeeper has to decide where to jump. There's not enough time to react to where the ball has been kicked. So it's a strategic game in this sense as well. Can be analysed. I think Philip Sinclair has a third-year project on analysing penalty kicks, if anybody's interested in that. Okay, I'll put one last one, which is a multiplayer game, and it's a kind of a strategic game, but not exactly. But it's an example. Is deciding. So it's drivers deciding which route to take. Okay, and the payoff depends on congestion. So if everybody decides to take the same route, it'll be very congested. Whereas if they split, then they're generally going to be better off. Okay, it seems like my time is up. So bring your handout next week because there are still some unused slides, and we'll continue with this.